Hello students, today we will see solutions theory part 3. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the same. In this class, we will try to explain the Raoult's law. Okay, so we will see what is Raoult's law, some examples of it, as well as the equation related to this Raoult's law. To understand Raoult's law, you must know that what is the Vapour pressure in a liquid-liquid solutions. Then we will try to compare the Raoult's law with the Henry law and see that what a beautiful analogy is between these two laws. Coming on to the Vapour pressure of the solutions of solids in liquids. Then at last we will cover example of numerical related to the Raoult's law. To understand Raoult's law, first you should know that what type of solution is there for the application of Raoult's law. So Raoult's law can be only applied to liquid solutions, and if I talk specifically, it should be applied to liquid-liquid solution. First, I will make you understand that what is liquid solutions. We have already seen the example of it. So to get a glimpse of it, you can think of liquid solution as a solution in which the solvent is a liquid. Okay, the solvent is a liquid. We are not trying to define the state of solute right now. So the solute in the case of liquid solution can be in any of these three states, like your gas, liquid or solid. The important point is that your solvent should be liquid. So solution can contain more than one volatile component, and generally the liquid solvent is volatile. Okay, so this is a very important point for the application of Raoult's law, that your solvent should be volatile. Okay, but your solute may or may not be volatile. Now what is the meaning of volatile here? Volatile means the substances which can be vaporized easily. Those substances are termed as volatile. Clear? Now, to understand this Raoult's law, you must know that our Raoult's law is only applicable onto the liquid-liquid solution. And in the Raoult's law, we will try to develop a relation between the Vapour pressure of liquid-liquid solution with the concentration of the solute. For that, we will consider a binary solution. What is a binary solution? A solution which contains only two components. One is solvent and other is solute. And out of this, one is volatile in nature. Okay. But here what we are considering is that both of the liquids are volatile, and we are naming those components as 1 and 2. Again, what is volatile? The substances which can be converted to vapor easily. If you take these two components which are volatile in a closed vessel, then as I have already mentioned, since they can be vaporized, so they will evaporate and eventually an equilibrium will be established. Okay, so they will start to evaporate, and at a point the rate of evaporation, means the going of liquid into the gas phase, and the rate of condensation, the gas phase going to the liquid phase, becomes equal. And in this way we get a equilibrium stage between the vapor phase and the liquid phase. Now at this point we are considering that the gas phase which is present upon the liquid solution has a vapor pressure equals to P total, where P1 and P2 are the contributing factor to this P total, and P1 is the pressure due to component 1 and P2 is the pressure due to component 2. So you have to remember all of the assumptions, that you are taking a liquid-liquid solution, and second thing we are thinking is that your both of the liquids are volatile in nature. Till now, we have considered three things: total pressure above the liquid surface, partial pressure of 1, and partial pressure of the component 2. Now, this partial pressure is related to the mole fraction, which is chi1 and chi2 of the two components 1 and 2 in the liquid phase. Okay, so we are considering the mole fraction in the liquid phase and trying to develop a relation with the partial pressure of the gas which is in the vapor phase of the same component. Now, this relationship, which we will see in the next upcoming slides, is the quantitative relationship, and is known as the Raoult's law. What does Raoult's law states? It states that the solution of volatile liquids, again, see, we have taken volatile liquids, the partial pressure of each component is directly proportional to the mole fraction present in the solution. So, the vapor pressure that has been developed upon the liquid solution is directly proportional to the mole fraction of each of the components that are present inside the solution and are volatile at the same time. I hope we are getting the point here. So, if we apply this law on the component 1, which is volatile, we can write P1, that is partial pressure of 1, is directly proportional to the mole fraction of 1. If we remove this proportionality, we will get a proportionality constant, which will be the vapor pressure of the pure substance A. Now, what is this pure substance 1? Okay, what is this pure substance 1? It is the vapor pressure when we take that same component 1 in the pure form. Okay, we are not taking it in the solution phase and we are taking it in the pure form, and whatever will be the vapor pressure at that time will be taken as P01. So this is our proportionality constant here. And this should be P01 should be seen at the same temperature, on the temperature which we are observing the solution. Now, this same analogy can be applied onto the component 2. So we can write P2 equal to P02 chi2. Similar to this, and this is our Raoult's law, which says that the partial pressure of the component is directly proportional to its mole fraction in the solution phase. And here also we have this P02 as the partial pressure of the component 2. Now we have another law named as the Dalton's law of partial pressure. This law says that the total pressure in a vapor phase is equals to the sum of the partial pressure of the components. Now, what is the meaning of this? Suppose we have a gas enclosed in a balloon, and the gases that are enclosed in that mixture are nitrogen, oxygen, and sulfur. Now, each of these molecules will have some pressure. So we can write that pressure due to oxygen plus pressure due to nitrogen plus pressure due to sulfur is equals to the total pressure. Now, we can say the same thing for P1 and P2, since only 1 and 2 are present here. Therefore, P total can be written as P1 plus P2. So, P total is equals to P1 plus P2, where P1 and P2 are the partial pressure of component 1 and 2 in the given solution. Now, in the next part, we will substitute the value of P1 and P2. If we do so, we will get our total pressure as chi1 P1 naught, okay, and chi2 P2 naught. So these are the relations of the Raoult's law. Okay, we have taken the value from there of P1 and P2. Second thing what we have done, since it is a binary solution, that means chi1 plus chi2 is equals to 1. As you know that if you add all the fractions, you will get 1. You can take the example of cake, just cut it into 2 halves. If you add both of these halves, you will get 1. So that same analogy says that the chi1 plus chi2 will be equals to 1. Now, if it is true, then we can also say that 1 minus chi2 is equals to chi1. If chi1 plus chi2 is equals to 1, then 1 minus chi2 is equals to chi1. So we have substituted that value here. Now, simplifying this further will give us P01 plus P02 minus P01 chi2. Now, what we have done in this step? So, we have first of all multiplied the P01 onto 1 and P02 onto chi2. Okay, so this is very obvious. It is a simple, you can say, arithmetic calculation. Then, what we can see, if you multiply, so we will see that P01 minus P02 chi2 plus chi2 P02. So we have a chi2 common in both of this. So we have taken the chi2 common, and our final equation goes like P01 plus in the bracket P02 minus P01 into chi2. So this is your final equation, and here you can see that our P total and chi2 are related to each other. This equation looks like your equation of straight line, and for this we will see the graph in the coming slides. Remember, if you just compare it with the equation of straight line, then equation of straight line goes like y is equals to mx plus c. So y is P total, mx, so mx has this whole term, and c has this P01. Okay, so m is the slope here, so that will be equals to chi2, and x is the P02 minus P1. Now you can say that the intercept will be P01. Okay, so this is not m2, chi2 is not the m2, P02 minus P1 is the m2, chi2 is the x. Okay, chi2 is our x. So if we plot a graph between P total and chi2, we will get a slope whose intercept will be equals to P01. We will see this graph. Now, before moving on to this graph, let us draw some conclusions on what we have discussed till now on the Raoult's law. First thing is that the statement says that the total pressure, vapor pressure, can be related to the mole fraction of any one component. So in the previous equation, we can see it very clearly that we need only mole fraction of the second component to define the total vapor pressure. You can substitute the same for chi1 also and get it a direct relation between the total pressure and the mole fraction of the first component. So this is a very, very important point. Now, what is the second thing? Second thing is that the total pressure over the solution varies linearly with the mole fraction of the component 2. Or if you substitute it for the component 1, we may say the same thing, that it will vary linearly with the mole fraction of the component 1, for which we will see a graph. And the last and the most important point, that depending upon the vapor pressure of the pure component 1 and 2, the total pressure over the solution decreases or increases. Now, to understand this point, you must see the graph to get a more clear picture. But what is written in this sentence, I will try to explain it without seeing the graph so that you can quickly grab the concept upon seeing the graph. So this line is saying that the P total, which the plot which we will get, it will increase or decrease depending upon the volatile nature of 1 and 2. Let's see the graph now. So this is your graph, and it is very important to understand this graph. So I said we will try to plot a graph between P total and chi2. So you can see here that as the chi2 is given here as 0, okay, and chi1 is given here as 1. What is the meaning of this? It says that initially at the left hand side we have only and only the component 1 present in the solution. So all of the pressure will be equal to the pressure due to 1, and that is the pressure of the pure component 1. Therefore, at this point, the pressure will be equal to the pressure of the pure component 1. Similarly, on the right hand side, we can say the same thing for the chi2. So here the pressure will be only due to the component 2. Now what we are doing in this intermediate thing? We are slowly increasing the concentration of 2. So from chi1 to chi2, if you see that chi2 is slowly increasing, okay, it is increasing, and on the right hand side we have only 2 present as the component and 1 is been diminished at this point. Now due to this, the partial pressure due to 2 is rising from left to right, and from right to left the partial pressure of 1 is rising as we are increasing the mole fraction of 1 from right to left. So this is very obvious, okay. Now one more important thing. If you see here, then P02 is present at a greater altitude as compared to the P01. It means the pressure of the pure component 2 is greater than the pressure of the pure component 1. And it is the reason that as we are increasing this component 2, we are seeing a total increase in the pressure, okay, because total pressure will increase on adding more and more volatile substance and remove less volatile substance, which is one component here. So 3 plots can be seen. First, the P1 is decreasing as we are decreasing the concentration of 1. The P2 is increasing as we are increasing the concentration of 2, and P total is increasing as we are adding more and more volatile component 2. So this thing is clear, I guess. So the same line is written here. These lines pass through the point for which chi1 and chi2 are equal to unity. So this is unity on the left hand side for 1 and unity on the right hand side for 2. So as expressed earlier, the P total versus chi2 is a linear graph. Okay, so this is a linear graph, and the minimum value of P total is how much? It is P01. Okay, and the maximum value is P02 due to increase in the number of molecules of the pure volatile component 2. So we can say that the component 1 is less volatile than component 2. Therefore, P02 is greater than P01. Now, the composition of the vapor phase in equilibrium with the solution is determined by the partial pressure of the components. Okay, so here the total pressure is being defined with the help of partial pressure at 1 and 2. Next is a very unpopular equation, but it is very helpful in solving numerical, because most of the students are focused on this Raoult's law equation and they forget about this very important equation and its significance. Now, the chi1 and chi2 that we are discussing were the mole fraction of the component 1 and 2 in the solution phase. But what about the concentration in the vapor phase? For that, we represent their mole fraction with y1 and y2. Okay, so in the vapor phase, the mole fraction will be equals to y1 and y2 of the two components 1 and 2. Now remember the difference between these two. that chi1 and chi2 are the vapor pressure in the concentration in the liquid solution, whereas y1 and y2 are in the vapor phase. Then if we use the Dalton's law of partial pressure again, we can say that P1 equal to Y1 P total, where Y1 is equals to the pressure, a mole fraction in the gaseous phase, and P total is the total pressure that we were discussing earlier. And P1 is the same partial pressure due to 1. Only the new term introduced here is Y1. Now, similar thing can be said for the second component. So, P2 will be equal to Y2 P total. Now, this thing can be generalized for a multi-component system and be written as the partial pressure of the ith component is equals to the mole fraction of the ith component in the vapor phase multiplied by the total pressure. Clear? So this equation is very, very important for you, as it is quantifying the concentration of the component 1 and 2 in the vapor phase above the liquid solution. Now, moving on to the next thing. So this is somewhat difficult to understand for some students. It is the topic of Raoult's law as a special case of Henry's law. So according to Raoult's law, the vapor pressure of the volatile component in a given solvent solution is given by Pi into chi Pi. We know this equation very well. Okay, this equation is very well understood now from our previous discussion. And for the solution of gas in a liquid, so initially this was for liquid solution. This is Henry's law, and we know it that it is for the gas in a liquid. It says that the solubility can be given as P is equals to Kh chi, where chi is the mole fraction of the gas in the liquid, P is the pressure of the gas, and Kh is the Henry constant. Now look at these two equations given here, which are of Raoult's law and Henry's law respectively. Now if we compare these two equations, we can see one thing common, that they both have the pressure term and the mole fraction or the concentration term. Okay, but the difference is of the Henry constant and the P naught I, that is of the proportionality constant. So proportionality constant is different for both of these equations. So we can say that these two equations can be written in a more general way if we write it as pressure is directly proportional to mole fraction. Now depending upon the phase or the components, we can take the Henry constant or the mole fraction. Hence, Raoult's law is nothing but a special case of Henry law, where your Henry constant is equals to the partial pressure of the pure component 1. Okay, it is the pressure of the pure component 1. So this is very important to understand. I guess you are getting the point of this similarity in Raoult's law and Henry's law, and you are just try to appreciate that Raoult's law is nothing but a special case of Henry's law, where your Kh become equals to the P naught I or P naught 1 if it is component 1. Now, another important class of solution is our solids in liquids. For example, if you are dissolving the table salts, sodium chloride, into the water, or your glucose or your cane sugar in the water. So these are all examples of solids in a liquid. You can also take the example of sulfur dissolved with carbon disulfide. So the physical properties of these solutions are different from the pure solvent. Okay. So there will be a change in the boiling point, melting point, and your appearance, density upon the addition or introduction of the solids in liquids. And this is very, very obvious as the intermolecular interaction is disturbed. For example, if we take the vapor pressure as a function, then liquid at a given temperature vaporizes under equilibrium condition when the pressure exerted by the vapors of a liquid over the liquid phase is called the vapor pressure. So what is vapor pressure? So the pressure that is exerted by the vapors of the liquid over the liquid phase. So whenever you are keeping a liquid in a closed vessel, its vapor will be formed above the solution, and that vapor will apply some pressure on the surface, and that is termed as the vapor pressure. So you can see the example of it in the diagram A, where we have the pure solvent only. The blue molecules which are far apart are representing the gaseous phase. Now this individual molecule will go and strike the surface, liquid surface, to create a pressure, and that is termed as the vapor pressure. Now in the next part, what we are doing is we are introducing a solute which is less volatile because it is a solid particle. Okay. And in general, solids are less volatile than liquid. Now what will happen as a result? Initially, if suppose these are 10 molecules that are exposed to the environment for evaporation. After the addition of solute, some of the upper side of this pure solvent are now occupied by a non-volatile solute, and it decreases the exposure of solvent molecule to the atmosphere, and as a result of it, now less number of these blue molecules are present as the gas phase, resulting in a less vapor pressure. So this is very important to understand that how these green particles or the solid particles are decreasing the you can say condensation evaporation process of this blue particles by interrupting their exposure. So we can see here, with the help of the occupation of the entire surface of the molecule of the liquid with the solid particle. Hence, we can say it that if we add a non-volatile solute to a given solution, the vapor pressure of the solvent decreases and it is less in the formed solution. So, at a given temperature, it is always less than the pure solvent. Now, if we try to redefine the thing that I have discussed earlier in points, then the surface has both solute and solvent particles. Since the fraction of the surface covered by the solvent molecule gets reduced, as a result, the number of solvent molecules which are escaping gets reduced, and now we have a reduced vapor pressure. So you can explain our whole lecture about this lowering of vapor pressure with the help of this when we will discuss this colligative property in more detail. Now, the decrease in vapor pressure of the solvents depends upon the amount of non-volatile solute that we are adding. More the number of volatile solute, less will be its vapor pressure, as more and more surface sites will be occupied by this solute particles. And this lowering is independent or irrespective of the nature of the solid particle we are taking, as long as it is non-volatile. For example, if we take a non-volatile component like sucrose and add it to a more volatile water, which is 1 kg in mass, then it is nearly similar to that produced by adding 1 mole of urea to the same quantity of water at the same temperature. Okay, so there is a decrease in a vapor pressure. Now, if we try to define Raoult's law in a general form that for any solution, the partial pressure of the volatile component, remember, it is defined for the volatile component, and in the liquid solution, this thing is directly proportional to the mole fraction. Our vapor pressure is directly proportional to the mole fraction, given that the volatile component should be considered while considering the mole fraction. So this was all about the Raoult's law. Now, coming back to the solids and liquids. So we are taking an example of solvent 1 and solute 2. So when the solute is non-volatile, only the solvent molecules are present in the vapor phase and contribute to the vapor pressure. Let P1 be the vapor pressure of the solvent Chi1 and P01 will be the vapor pressure in the pure state. Then according to Raoult's law, if we apply the Raoult's law for solids in liquids, so initially we were applying it to the liquids in liquids, now we are applying it to the solids in liquids. And since only the first component is volatile, we can apply it for the first component only and not the second component. So we can write P1 is directly proportional to Chi1, or P1 is equals to Chi1 P1 naught. Removing the proportionality constant, we have introduced P01, and this is of the vapor pressure of the pure solvent 1. So this equation is same as the equation which was formed in liquid-liquid solution, but here the care should be taken that we are only considering the solvent molecule which is more volatile and not the solid particle which is non-volatile in nature. Now, if we plot a graph for this type of solution, we don't have to worry about the mole fraction of the second component, as it has no pressure, because solids are not applying pressure on the side walls of the container that we have kept it in. With that thing in your mind, you will get a straight plot for a solid and liquid solution where this vapor pressure is increasing, and it is only due to the increase in mole fraction of the solvent, which is liquid and more volatile. Now let us see a question which is related to our overall discussion. Our question is the vapor pressure of chloroform and dichloromethane at 298 Kelvin and 200 mmHg and 415 mmHg. So these are the respective vapor pressure of what? Chloroform and dichloromethane. Now, since they are of the pure component, we have to use it and find the vapor pressure of the solution, which is formed by mixing 25.5 gram of chloroform and 40 gram of dichloromethane at the same temperature, which is 298 Kelvin. And second thing, we have to calculate the mole fraction of each component in the vapor phase also. First, we will look at this vapor pressure of the solution. So what we will do in this? We know that the molar mass of dichloromethane can be calculated by calculating the individual contribution of each atomic weight of carbon, hydrogen and chlorine. So that comes out to be 12 into 1 plus 1 into 2 plus 35.5 into 2 for chlorine, which is equals to 85 gram per mole. Now what is the number of moles of this dichloromethane? How we will calculate it? It will be given mass by molar mass. So before moving on to that calculation, we will see the calculation of molar mass of chloroform also. Again, it's very simple. 12 into 1 for 1 carbon, 1 into 1 for 1 hydrogen, and 35.3 into 3, 35.5 into 3 for the chlorine. That will give you 119.5 gram per mole. Now coming back to the moles of CH2Cl2, it will be calculated as given mass 40 gram by molar mass 85 gram is equals to 0.47 moles. Similarly, the moles of chloroform can be calculated by using the given mass by molar mass, which we have calculated here. This will equals to 0.213 moles. Now we have the moles of dichloromethane and the moles of chloroform. Therefore, the total number of moles will be 0.47 by plus 0.213, which is equals to 0.683 moles of the given the given solution. So this is the total number of moles, including the solute and the solvent. If I ask you what is the solvent here, you will quickly say that it should be dichloromethane, as its mole fraction is high. Then the mole fraction can be calculated as, so whose moles is high, not the mole fraction, the moles is high. Mole fraction can be calculated as the moles of dichloromethane divided by the total number of moles, giving us the mole fraction as 0.688. Similarly, for trichloromethane, okay, for trichloromethane, we can subtract 0.688 from 1 and get it as 0.312. Again, this is the application of mole fraction, chi1 plus chi2 equals to 1. Now, using the equation, which is P total is equals to P01, P02 minus P01 into chi2. P01 is how much? It is 200 mm of Hg. P02 is 415 and chi2 is 0.688. This will give you 347.9 mm of Hg. So we have calculated the total pressure here. But are we interested in this? We have to calculate the vapor pressure of the solution. Yes. So we have calculated the first part. Now what about the mole fraction in the vapor phase? So this can be calculated as Y1 is equals to P1 by P total, where Y1 is the mole fraction in the gas phase. We have seen this equation and I have mentioned it already that it is important. If we know that 0.688 multiplied by 415 gives us the partial pressure due to the CH2, Cl2, then we can calculate it for the dichloromethane from the Raoult law directly. What will be the partial pressure of chloroform? Using the same calculation, we can get it as 62.4 mm of Hg. Now, coming back to our important discussion of the mole fraction in the gaseous phase, it will be given as the partial pressure of the dichloromethane divided by the total pressure, which is 347.9. This will come out to be 0.82 as the mole fraction of dichloromethane. Now, what will be the mole fraction of chloroform? Again, take the pressure of the partial pressure of the chloroform divided by the total pressure, which is equals to 0.18. You can directly get this 0.18 by subtracting 0.82 from 1. So we can see here that your partial pressure of the dichloromethane is more due to the more volatile nature, as its pressure in the pure component form is 415, whereas in the chloroform it is 200 mm of Hg. So, since the vapor phase is also rich in CH2Cl2 due to this reason. Now we can conclude that at equilibrium, the vapor pressure will reach in a component which is more volatile in nature. So our vapor phase is more rich in the more volatile component. So this was all for today's class. Thank you.